Hello students. So in the last lecture we have discussed some numericals regarding analysis of T-beams. We will be seeing further more numericals. Those were the basic numericals that we have seen in the last video. We will move towards some advanced numericals. So this is our first numerical of today. The question is, determine a factored moment, that is mu, for a T-beam having following requirements. The width of flange is given as 1500 mm, that means it is mentioned as BF. Width of rib, again rib, that is web. So width of web is given as 300, that is our BW. Depth of flange, that is our DF. The value of DF is given as 100 mm, and the overall depth is given as 650. So overall depth, that means our capital D. So capital D is given as 650 mm. Total reinforcements are given as a composite reinforcement. Now this is a typical sum here. It is given as a composite reinforcement which carries two different composition of bars. For example, the total number of bars mentioned here are 8, and that comprises of 6 numbers of 28 mm and 2 numbers of 22 mm bars. So the total number of bars will be 28 mm will be of 6 numbers and 22 mm diameter will be of 2 numbers, and the effective cover is given as 50 mm. So small d will be 600 mm. The grade of concrete is M20 and Fe415. So while finding AST, again there are two methods. You can either use manual calculation or from steel table. Manually you can solve by adding these two things. That is, the first case will be 6 into pi by 4 28 square plus 2 into pi by 4 22 square. But it will be easy if you look upon the steel table. So moving forward from steel table, we can directly see these values. 6 numbers of 28 mm dia, that means we will see the row having 28 dia and the column having 6. So the value will be 3694. So our first value will be 3694. So 3694. And the second one will be 2 numbers of 22. That means we need to add these two values. 2 numbers of 22, that means 760. So we'll be adding these two terms to get our total AST. So whenever composite reinforcements are given, we need to find the total AST or total reinforcement using this method. So here, solving this, we'll be getting an answer. Total AST equal to 4454, that is 44.54 centimeter square or 4454 mm square. And as in question it is not mentioned that which section is given, either it is a balance section or not. So the first step will be to calculate the value of FC and FT. FC being compressive force will always be equal to 0.36 FCK BF DF. So first thing we will be finding FC. 0.3 FCK is given in question as M20, BF is given in question as 1500 mm, and DF is also given in question as 100. So solving this, we get an answer 1.08 into 10 raised to 6 Newton. And the second thing will be to find our tension force, that is FT. So FT will be 0.87 F by AST. AST we have calculated here. So substituting it, the value comes out to be 1.608 into 10 raised to 6 Newton. Again, I am elaborating this thing. Keep in mind the power of both the values, that is both the forces should be same. If it is not the same, then both the forces will not be correctly representing the values and the relation could not be obtained properly. So keep in mind while solving these cases, the power should be in the same form, or it will be better if you write the full value and then compare both the cases to get the proper answer. So in this case, I'm getting an answer FC is less than FT. Now FC is less than FT, that means tension force is more, and we already discussed this thing that whichever force is more, the CG or neutral axis will be shifting to that zone. So here tension force is more, so the CG will be shifting or neutral axis will be shifting to the web portion. So here neutral axis will be in web. The previous sum that we have discussed in the last lecture was that it contained the neutral axis is in flange zone, and here we have seen that neutral axis is in web. So while neutral axis is in web, the XU will always be greater than DF. For example, consider this as a T-beam, this being our DF, that is depth of flange. If the neutral axis exists somewhere around here, then this will be our depth of neutral axis, that is XU. So from this relation you can definitely say that XU is greater than DF. So now we'll be using the case XU is greater than DF. So from page number 96 of your IS code, you will be seeing this value. This value will be in the next page, that is page 97. So from page 97, now we will be referring G 2.3. In the last video we have referred G 2.1 and 2.2. Now we will be referring G 2.3. So first we will be looking at the statement. It states that for XU max greater than XU greater than DF, we have just proved for half of the relation, that is XU is greater than DF, we have proved here. The second half, that is XU max also should be greater than XU, that we will be proving later on. The moment of resistance may be calculated by the equation given in G 2.2. Means for G 2.3 there is no new equation. You need to refer the equations for the limiting section only. But how, we will see here. Let us visualize the whole thing together. This equation is given in page 96 and these both cases are given in page number 97. We will be referring this case, that is G 2.3 for now, as it is getting an answer XU greater than DF. So here for XU greater than DF, the moment of resistance may be calculated by the equation given in G 2.2. That is, either we will use this equation or we will use this equation. If we are getting answer XU greater than DF, then we will be using these two equations to solve these things. But how and when to use this equation? For this we need to refer the clause further on. We need to use G 2.2 when DF by XU does not exceed 0.43. So a new ratio is to be obtained, and this new ratio is DF by XU. So for G 2.3 we will be calculating the ratio DF by XU. DF, that is our depth of flange, and XU is depth of neutral axis. So we will be comparing the or relating this ratio DF by XU. If it does not exceed 0.43, that means if it is less than or equal to 0.43. If we get ratio DF by XU less than or equal to 0.43, we will be using this equation to find MU. Clear? If we get an answer DF by XU is less than 0.43, we will be using this equation to obtain our MU, that is moment of resistance. And if we get an answer DF by XU, that is in the we can see in the clause that and G 2.2.1 when DF by XU exceeds 0.43. That means if we get an equation DF by XU greater than 0.43, then we will be using this equation. So this equation is used when the ratio DF by XU comes out to be equal to or less than 0.43, and this equation will be used when the ratio DF by XU is exceeding 0.43. That means it is greater than 0.43. Clear? But the most important thing to be remembered is given in the last line. So see it again. It is mentioned in both cases substituting XU max by XU. Means if we are using G 2.3, then we will be using either this equation or this equation. But for using G 2.3 case, we will be substituting in both cases XU max by XU. So in the equation, the value of XU max will be substituted by the term XU. We will see in this sum that how it is related. So moving further, to find XU. Now XU cannot be obtained from any equation given in the IS code pertaining to clause G 2.2 or 2.3. Clear? So we need to find XU using the conditions of equilibrium that we have used in the doubly sections. So for finding XU, whenever we get the case that XU is greater than DF and we need to find XU, then XU will always be calculated using the condition of equilibrium, that is C equal to T. Here we can see that C1 is plus C2 equal to T. There is no such case as T1 or T2 regarding flange beams. So directly we can say that C1 plus C2 equal to T. C1 will be the portion of singly and C2 will be compression force due to the flange section. So C1, as we have seen in the stress strain diagram, was 0.36 FCK BWXU and C2 was 0.45 or 446. You can write either both of them, both are valid. FCK BF minus BW into DF and T will be 0.87 FIAST. So in this whole equation, the only unknown that is remaining is XU. So we'll be getting XU using this equation. So XU comes out to be 244.44 mm. Clear? Now we'll be finding XU max. XU max again from the same case as we have used in the previous sums and previous chapters. We will be getting it from page number 70. So from page number 70 we will be getting this answer and we can get the relation that XU is less than XU max. Now coming on to the third case that we need to refer. Here we have seen that XU was greater than DF, but we also need to prove that XU max is also greater than DF every time if we are using G2.3. If we are using G2.3, we need to compare all these three cases. Yeah. So here we can prove that XU max is greater than XU. So we can move further ahead. So now we will be solving this ratio, or we will be finding the value of this ratio, that is DF by XU. So DF by XU, DF was 100 mm, XU we can see here that it comes out to be 244.44 mm. The ratio comes out to be 0.409, and as it is less than 0.43, here we can see that when DF by XU does not exceed 0.43. So here in this case also DF by XU does not exceed 0.43. So we will be using G2.2 to solve the equation of MU. Yeah. So we'll be using this equation to solve our answer of MU. But again keep in mind XU max will be substituted by XU. So in this equation, wherever you see the term XU max, you have to mention XU in this case. So solving it, we get an answer 856.58 kilonewton into meter. This equation is as per our IS code. So while substituting the value, we will keep XU in this and we will also keep the value of XU in this while solving our numerical portion. Clear? So this will be our answer, that is MU equal to 856.58 kilonewton into meter. Moving on to the next sum. The question is, a flange beam has following dimensions. The dimensions are given: width of flange, that is BF is mentioned, width of web, that is BW is also mentioned, thickness of slab, that is depth of flange, and overall depth of beam, that means capital D, is given. Effective cover is 50, therefore the depth will be 450 mm. Tensile reinforcement is directly given, so there are no need to identify any number of bars or the bar diameter. AST, the value of AST is directly given in question, and we need to find MR, that is moment of resistance. We need to take M20 concrete and Fe415 steel. So while solving our answer, every time the first step will be to calculate the value of FC and FT. So in this case, FC comes out to be 864 into 10 raised to 3 Newton, and FT comes out to be 102 into 10 raised to 4 Newton. Or you can write this whole number in the format and you can compare both the equations. So here we can see that FC is less than FT or FT is greater than FC. So tension force is more as compared to compression force. So the neutral axis is in web. Clear? Neutral axis is in web and XU is greater than DF. It is similar to somewhat we have solved the previous example, but change will be incorporated now. So we will be using this equation, that is XU is greater than DF. So for XU is greater than DF, again we will be solving the ratio DF by XU. If DF by XU is greater than 0.43, we will be using the equation 2.2, and if DF by XU is less than or equal to 0.43, we will be using the equation 2.2, and if DF by XU is greater than 0.43, we will be using 2.2.1. So we will see in this case that what is the value of DF by XU. So we'll be finding XU first. So XU can be obtained from the equation, that is C1 plus C2 equal to T. XU comes out to be 122.54 mm. As DF was 100, so XU is greater than DF is satisfied here, and hence it is safe. Now we need to find the equation of XU max. As it is given Fe415 steel, XU max will be 0.48 D, which comes out to be 216. Here we can also compare that XU max is greater than DF. So the whole relation is been satisfied, that is XU max greater than XU greater than DF. To imply our equation 2.3, this whole equation is to be satisfied. What if not satisfied? We will see in the further lectures. So now we will be solving the equation DF by XU. DF was 100, XU comes out to be 122.54. So the value here is 0.81, and 0.81 is greater than 0.43. In this last numerical we saw that the DF by XU ratio comes out to be less than 0.43. In this case, DF by XU ratio comes out to be greater than 0.43. So again, moving on to the equation, if DF by XU exceeds 0.43, we will be using G 2.2.1. Clear? So moving on to G 2.2.1, we will be using this equation. Now in this sum, we will be using this equation. Again, keep in mind, for G 2.3, we always need to substitute XU max by XU. So we will be substituting XU max by XU, but we will be using this term. In this term, you will see a new parameter that has been used, which is not being used in G 2.2, that is YF. Here you can see the term YF being used, and in the previous term it was DF. DF we already knew that it is depth of flange. YF is effective depth of flange. Yeah, YF is effective depth of flange. Means, for example, if this is a T-beam, this whole section will be our DF, but as it is a component of slab, for certain cases the whole slab portion won't be acting as a compression member. Some portion or some distance will be acting as a portion of slab. So in that case, suppose up to a certain level, up to this level, or you can say that this portion is only acting at the compression zone. The bottom layer is not acting at the compression zone of slab. It is acting at to be a beam. So this distance is called YF. That is effective depth of slab. It is not pertaining to every sum. It can be regarding upon what the data are being given. So this is the distance YF. YF will always be less than the value DF. Yeah. So when to use YF and when to use DF is to be predetermined by you. In this case, we will be using YF, and the equation of YF is also given here. You can see that YF, to find YF, the equation is also given in the IS code. It is equal to 0.15 XU plus 0.65 DF. XU and DF we have already seen. XU we have calculated and DF is given in the question. So YF comes out to be this value, and YF by solving this equation comes out to be 96.38 mm, which should always be less than DF. Keep in mind, YF, that is effective depth, should always be less than DF. So in this equation now we will be substituting YF, that is 96.38. This is the only change between G 2.2 and G 2.2.1. Else all the equations are, or all the parameters are same. The only change is that in G 2.2 we'll be substituting DF, and in G 2.2.1 we'll be substituting effective depth of flange, that is YF. And keep in mind again, we will be using XU in the place of XU max. Clear? So on solving this, we will get an answer mu equal to 349.45 kilonewton into meter. So this was our example pertaining to the case XU exceeds DF, that is XU is greater than DF. So we will see further more numericals in the next lecture. Thank you.